Welcome. Today I want to talk about quivers. These are graphs where also multiple connections are allowed and self-loops are allowed. If we see the proof of the theorem which we have seen last time is much simpler if we just enlarge the class of objects. And we will see why in a second. But first of all, about quivers, they appear in many places. Mathematicians consider finite categories as a quiver. It's a graph, it's a geometric structure also. It appears in applications like in chemistry. So, for example, this is CO2 here. H2O, that's water. H2O, that's the carbon, linear carbon molecule with a carbon atom, and then there are double bonds to the oxygen atoms. So there are some other things. This is a graph, which is a star graph, which is a carbon hexachloride. So here is a nice graph. This is some amino acid which is used in protein build-up, and so we see there's naturally a multiple connection here appearing. This is an acid which appears in vinegar. So today I want to look a little bit at the mathematics of quivers. The mathematics is very similar than the mathematics for finite simple graphs. Even so we have multiple connections which can appear, even so we have self-loops which can appear. So here I have an example. Actually, this is the example graph example quiver I want to discuss. So what we have here, we have a couple of vertices, finitely many vertices, n vertices. We have n edges, m edges, and these edges can be also multiple connections like here. So 1, 2, 1, 2 appears twice here. So this is a double connection, and then we have also a loop, a self-loop here. So this is an example of a quiver. And then we can define, like for graphs, we can define a gradient. And the gradient gives you, from a function on vertices, gives you a function on edges. So that's an exterior derivative, and I call it here f and not d. A rectangular matrix, a m times n matrix, and it's defined like that. If the edge is AB, then it connects with the AB. A is -1, otherwise it's 1. And if it's a self-connection, then it's 1. And so this is a n times m. And then when you take the transpose, you get the n times m matrix. So like in the case of simple graphs, we have also for quivers, we have a Kirchhoff matrix. And so we can look at the eigenvalues. And this Kirchhoff matrix has, again, the same structure than the Kirchhoff matrix for finite simple graphs. It's a diagonal, it's a diagonal part with a vertex degrees, and then adjacency matrix. Adjacency matrix of 2 is only non-zero for 2 different vertices, and it's -1 if they are connected by a single one. It's -2 if they are connected by 2, and so on. So here we have an example. If I take FTA, FTF, I get this matrix here. And so in the diagonal we have these DKs, these vertex degrees. So we can see that here quite clearly. So there is a vertex degree 4, which is here. So 1, 2, 3, 4, there are 4. Then we have a 3, which is here, 1, 2, 3. And then we have a vertex degree 2, which appears here. So this counts as one connection only. It's only one edge which is connected here, even so there are 2 coming, one coming in at the same time coming out. This counts as 1. So this vertex degree is of this vertex is 2, and then of course of these ones have each vertex degree 1. So I like this graph. It's the duck graph, right? You can see here ducky. The duck is swimming. And so this duck graph has this gradient, the transpose is the divergence, and then we have this Kirchhoff matrix, and then we have also the one form Laplacian. I talked about this last time, which is essentially isospectral, has the same eigenvalues, except one eigenvalue 0 is additionally here. So in this case, unlike the case of graphs, in the case of graphs, what we have is always the 0 eigenvalue. And in this case, the eigenvalue, the smallest eigenvalue is no more 0. But because of this form FTF, you can see that the eigenvalues are negative. Right? It's very, very easy to see. So if you have an eigenvector, and then we have a kv is equal to lambda v, and then you take the vector v has length 1, so you take v kv is equal to lambda, right? That's because it's lambda v, and v has length 1, so that's the same thing. Then v ftf v, which is equal to f v f v, which is of the form ww, which is bigger or equal to 0. So lambda, the eigenvalue, is always bigger or equal to 0. Even so, we have now a quiver, and we don't have a finite simple graph like this beautiful amino acid here, which is used in protein buildup. We have a quiver, not a graph, but still the eigenvalues are all non-negative. By the way, there's a theory in chemistry, this is related to chemistry, also in chemical graph theory. You are interested in the eigenvalues. So the eigenvectors, this is Kirchhoff theory, so you have quite a nice application of graph theory, very, very much down to earth, right? So graphs are very accessible objects. I think also quivers are very accessible objects, even simpler even in the definition, right? We don't even have to make any assumption that it's simple. We just don't make any assumption, and then we have actually a category, right? We have objects and we have morphisms between them, so it's quite a natural object, a quiver. It's used also in representation theory, many different parts of mathematics, so it's quite nice. But we have the spectral theory, looks essentially the same then for finite simple graphs, and I realized just when I did the last week's talk that actually this generalizes to quivers. So what I prove is, first of all, an upper bound. There's an upper bound which has been done by Anderson-Morley for the spectral radius for the largest eigenvalue. I generalize it to the arbitrary eigenvalues. So that's the first theorem. That's true for every quiver. Now, last time I did that differently, and also in the submitted kind of in the archive version of the paper, I have kind of just artificially as closed the set of matrices appear here, Kirchhoff matrices, and assumed we take a closure overall when we take principal submatrices. But that's a little bit awkward because these objects are the normal Kirchhoff matrices. Now, what is very nice, and that's the kind of the key lemma here, that's the reason why this whole thing collapses down to a proof, which is very, very simple. And I think it's actually a proof from the book, because you cannot make it simpler. It's just induction with respect to the n, the number of vertices. And what happens is when you take away a vertex, like for example for this duck, I take away the head of the duck, right? So it's a headless duck. Matrix is no more a Kirchhoff matrix of a finite simple graph. But what happens, it's the Kirchhoff matrix of still a quiver, and what happens is just this node here had been connected to that just gets another self loop. So what you have is just another, you actually just get a self loop here instead. So you add another self loop here. And so every node which is connected to that node which you have taken away gets a self loop. So you are in a larger class of geometric objects, but still all this spectral theory which we have used, especially supersymmetry relation between zero forms and one forms, works in the same way. So everything can be just by induction done much simpler. So what we assume then, we just first of all, for n equal to 1, it's no problem. When you have only one node, then you have just a couple of loops attached, and so the spectral estimate is trivial. But then you make the step from n to n plus 1, and that involves just the Cauchy interlace theorem. And so what happens is, if you take, this is the for the matrix K, right? And this is the matrix which is obtained when you take a principal submatrix, and you delete. And you delete, say, the third. If you delete the third row and third column, what happens is then you get the smaller matrix, n times n matrix. That's kind of which has eigenvalues mu 0 to mu 1 to mu n, and then you have immediately that the lambda k is smaller than mu k, which has then this estimate which you have. So when you are doing the induction with respect to the upper bound here, you just take away the vertex with the largest vertex degree, and so you have still that estimate here. But then there is one thing dangling off, right? This one you cannot bound by the old ones. This is the case n. This is the case n plus 1. You have to bound this, but this bound is just the spectral radius bound of Anderson-Morley, which holds in the same way here. So what happens in the case, this is the K1 matrix. It's a matrix on functions on edges, which is the one form Laplacian, and the one form Laplacian has always 2 everywhere where we have just an edge which is an unusual edge. If it's an edge which has a loop, then we have only 1 because it's only connected to 1. And these are all connected. 2 parts, 2 edges are. If you take 2 edges, one edge and another edge, you have a -1 or 1 depending on whether the orientation fits or doesn't fit. But what happens is you can estimate this column, the sum of the absolute values of the column element. That's Anderson-Morley's rule. You can estimate this by dk plus dk minus 1, or dn plus dn minus 1. So in the upper bound, you make the induction with respect removing the largest one, and then you get. So for every quiver, we have spectral estimates in the same way than spectral estimates for graphs. Let me just say something about finite structures. These are finite structures, right? Finite geometric structures. I'm always was working with finite simple graphs, and I like finite simple graphs because they come automatically with a kind of a nice simplicia complex. If you don't want to just restrict yourself to one-dimensional simplicia complexes, the Whitney complex makes geometry. For example, you can look at manifold structures, and talked about this a lot, about this. So graphs come automatically with a natural structure. So what happens then here, so this is a simplicia complex, which is a finite set of sets, which is invariant under the operation of taking finite subsets. So that's kind of one of my favorite structures, because there is only one axiom. For hypergraphs, which is just a finite set of sets, non-empty sets, that's actually the simple structure, which is also very popular, but you can do much less with hypergraphs than with simplicia complexes. There are more theorems for simplicia complexes than for hypergraphs. Hypergraphs are just too general, just a finite set of sets. But simplicia complexes have this invariance. And then there is a more general structure, which is simplicial sets, which actually appear here also. So every quiver naturally comes with a simplicial set. So I start to actually get warmed up more about simplicial sets. I never really liked CW complexes for building up things, because for these CW complexes you need kind of a history, you need kind of more. You cannot see just, if you look at an object, you cannot see what, you have to describe it as a dynamical object, so to have a CW. But also for quivers, what is nice about quivers, they are just very intuitive. You can understand them, as a kid can understand them, right? This is just a network, but now we can have also multiple connections, like for actually also for, say, street networks or trade networks or internet networks or so on. So you can have multiple connections between different nodes, or self-connections. And so it's also a very natural object, and also comes naturally with some objects which are kind of allow you to do topology. So something I have to look a little bit more. Maybe I'll talk a little bit more about this next time. By the way, it also, so next time I will probably talk a little bit about the Schrödinger case when you have and you also attach potential values, add a potential value energy at every node, and the estimate is exactly the same, because you can rewrite it as a quiver, approximated as a quiver. So that's it, what I wanted to say today.